A telescope pointed at empty sky, a patch of darkness smaller than a grain of sand, held at arm's length. Webb stared at it and found 164,000 galaxies hiding there. Some of that light left before our sun existed, before Earth existed, before anything you know existed. We're going to travel through the cosmic dawn, a galaxy born 280 million years after time began, a chemical mystery hiding inside the oldest stars, and a flaw in our universe so serious it may force scientists to rewrite everything. If you enjoy the journey, subscribe and hit like. It helps more than you know. Stay with us. We begin now. On Christmas Day, 2021, a rocket launched from the coast of South America, carrying the most expensive science instrument humans have ever built. $10 billion, folded up like origami inside a rocket nose. The James Webb Space Telescope rode that rocket into the dark, unfolded its golden mirror in the cold of space, and aimed itself at the oldest light in existence. Scientists had been planning this moment for 30 years. 3 decades of blueprints, arguments, budget cuts, delays, and one near cancellation that almost killed the whole project. But on that Christmas morning, it finally flew. Webb is enormous. Its mirror stretches 21 feet across, about the width of a school bus lying on its side. That mirror is made of 18 separate hexagonal segments, each coated in a microscopic layer of real gold. The gold is thinner than a human hair, but it reflects infrared light better than any other material on Earth. The telescope did not go to orbit around Earth like most space instruments. It traveled 1 million miles away from our planet. That is 4 times the distance between Earth and the Moon. Out there, Webb sits at a stable point in space where the gravity of Earth and the Sun balance perfectly, letting it hover in place without burning fuel to stay still. Before Webb launched, the best images of deep space came from the Hubble Space Telescope. Hubble changed how humans saw the universe. But Hubble was built to see visible light, the same kind your eyes detect. Webb was built to see something different entirely, something older, something Hubble could never reach. And the very first time Webb sent images back to Earth, astronomers went quiet. One team expected to find maybe a few faint galaxies in their test image. They found thousands, ancient light pouring in from directions nobody had looked carefully before. Galaxies so distant their light had been traveling since long before our solar system formed. Scientists describe looking at distant space as looking backward in time. Light travels fast, about 5.9 trillion miles every year. But space is so enormous that even at that speed, light from distant objects takes billions of years to arrive. When Webb captures that light, it is capturing a snapshot of the universe from billions of years ago. A genuine photograph of the past. One number captures how powerful this machine is. Hubble could see galaxies that formed about 800 million years after the universe began. Webb can see galaxies that formed less than 300 million years after the universe began. That gap sounds small. It is enormous. Those 500 million years are the most mysterious and least understood period in all of cosmic history. The era when the first star switched on, the era scientists call the cosmic dawn. Webb was built specifically to stare into that era, to catch the first faint glow of a universe coming to life. And what it found there rattled every assumption scientists had built over the last century. But before we get to those discoveries, you need to understand something strange about how this telescope actually works. Because Webb does not just point and click like a camera. It does something far more clever, something that turns light itself into a time machine. Picture a lighthouse 10 miles offshore on a foggy night. You see the beam sweeping across the water. But here is the thing, you are seeing that light as it was a tiny fraction of a second ago, because light takes time to travel. It is a small delay, unnoticeable. Now stretch that distance to billions of miles, then billions of light years. The delay stops being tiny. It becomes the most important fact in all of astronomy. Light travels at about 186,000 miles per second. That sounds instant. Across a room it is. Even across Earth, the delay is nothing. But the universe is so vast that light from distant galaxies takes billions of years to reach us. When Webb captures that light, it is capturing a picture of those galaxies as they looked billions of years ago. The sun is 8 light minutes away from Earth. The light hitting your face on a summer afternoon left the sun 8 minutes ago. You are always seeing the sun as it was 8 minutes in the past. The nearest star outside our solar system sits about 4 light years away. When astronomers look at it, they see it as it was 4 years ago. Now scale that up. The galaxies Webb studies sit billions of light years away. Looking at a galaxy 13 billion light years away means seeing it as it existed 13 billion years ago, back when the universe was young. The telescope is a time machine, pointed outward, aimed backward. Scientists call the snapshot of the universe captured by these ancient photons the observable universe. Everything inside that bubble is observable because its light has had time to reach us. Everything beyond that boundary is invisible and will always be invisible because the universe is expanding faster than that light can travel toward us. Webb sits at the very edge of what humans can detect. It catches the faintest, oldest, most stretched photons that exist. Photons so ancient they predate our sun by billions of years. This is where redshift enters the story. The universe has been expanding since the Big Bang. Space itself is stretching. As that space stretches, the light traveling through it stretches too. The wavelength gets longer. Longer wavelengths shift toward the red end of the color spectrum. Scientists call this process redshift. The older and farther a galaxy is, the more its light has been stretched, and the redder it appears. Hubble could detect moderately stretched light. Webb's infrared sensors detect extremely stretched light. Light so red it has moved completely beyond what human eyes can see. This is the key. Ancient galaxies from the cosmic dawn do not glow with visible colors. Their light has stretched all the way into the infrared range. Hubble was essentially blind to them. Webb was designed from the ground up to catch exactly this kind of light. Every galaxy Webb studies is a postcard from the past, a frozen moment from a universe that no longer exists in that form. The stars in those images may already be dead. The galaxies may have merged, exploded, or transformed beyond recognition in the billions of years since that light left them. And the farther Webb looks, the older those postcards get. The oldest one scientists have confirmed so far carries light that is 13.4 billion years old. What does a galaxy look like from that far back? The answer is both simple and strange. And it starts with a mirror covered in gold. Hold a flashlight behind a thick blanket. The light disappears. Now swap the flashlight for a heat lamp. Press your hand against the blanket. You feel warmth. Heat moves through fabric that blocks light. This is the basic idea behind infrared astronomy. Infrared is a type of energy similar to heat. It passes through materials that block ordinary visible light. Cosmic dust, thick gas clouds, swirling nebulas, all of them absorb visible light completely. But infrared radiation slips right through. This matters enormously for astronomy. The most interesting places in the universe are usually wrapped in dust. Stars are born inside dense clouds of gas and dust. Galaxies in the early universe were surrounded by thick blankets of material. Every telescope built before Webb that depended on visible light was essentially trying to see through that blanket. Most of the time, the view was blocked. Webb's mirror changes that completely. Those 18 gold-coated hexagonal panels collect infrared light and focus it onto sensors so sensitive they can detect the heat given off by a bumblebee at the distance of the moon. That comparison is confirmed. Scientists used it during Webb's design phase to describe the instrument's power. Gold was chosen for the mirror coating because it reflects infrared light better than silver, aluminum, or any other common material. Each segment received a coating 1,000 times thinner than a human hair. Gold that thin cannot be seen with the naked eye. The mirrors look faintly yellow, but the layer doing the actual work is practically invisible. The mirror did not launch as one solid piece. 18 separate segments, each about 4.5 feet across, folded together to fit inside the rocket fairing. Once Webb reached its destination, 1 million miles from Earth, those segments unfolded and locked into alignment. Engineers spent months adjusting each one with tiny motors. pushing them into position with accuracy measured in nanometers. 1 nanometer is 1/1000th of a meter. The result is a mirror that acts as a single surface, 21 feet wide. To put that in perspective, the Hubble Space Telescope mirror measures about 7.9 feet across. Webb's mirror collects about 7 times more light, 7 times more ancient photons, 7 times more information from the edge of time. But the mirror alone is not enough. Infrared light is essentially heat, and any warm object emits infrared light, including the telescope itself. If Webb operated at normal temperatures, its own body heat would blind its sensors, the way sunlight blinds someone staring directly at it. This created a massive engineering problem. How do you keep a telescope cold enough to see the universe's faintest heat signals without the telescope radiating its own heat into the sensors? The answer is the sunshield, a 5-layer membrane the size of a tennis court, and the most extreme refrigeration system ever sent to space. The sunshield blocks heat from the sun, Earth, and Moon simultaneously. On the hot side, temperatures reach about 230 degrees Fahrenheit. On the cold side, where the mirror and sensors sit, temperatures drop to negative 387 degrees Fahrenheit. That is close to the coldest temperature physically possible. And staying that cold is not optional. The moment Webb sensors warm up, they go blind. What exactly do those sensors detect at the edge of their sensitivity? Something even stranger than dust-piercing infrared. Something that forced engineers to solve a problem nobody had faced before. Picture a room so cold that air itself turns to liquid and then to frost on the walls. Now go colder, past the point where oxygen freezes, past the point where nitrogen solidifies. Almost all the way to the coldest temperature the laws of physics allow. That is where Webb's main science instruments operate. Absolute zero is the theoretical bottom of the temperature scale. At absolute zero, atoms stop moving. Nothing can get colder. Webb's infrared camera chills itself to within a few degrees at that limit, hovering around negative 447 degrees Fahrenheit. For context, the surface of the moon on the dark side reaches about negative 280 degrees Fahrenheit. Webb runs colder than the dark side of the moon. The reason comes down to what Webb is trying to detect. Infrared light is essentially heat energy. It travels through space as waves just like visible light, but with longer wavelengths. Webb sensors detect those waves by measuring the tiny amounts of energy they carry. The problem is that any warmth inside the telescope, even microscopic warmth from the sensors themselves, drowns out the signal. It is like trying to hear a whisper in a thunderstorm. Cooling the sensors nearly to absolute zero silences the internal noise. The whisper from 13 billion-year-old galaxies becomes audible. Webb achieves this through a combination of passive cooling and an active refrigeration system. The sunshield, that 5-layer membrane blocking heat from the sun, handles most of the work passively. Sitting in the shade of that shield, the telescope drops to extremely low temperatures on its own, but the most sensitive instrument, the mid-infrared detector, needed to go even colder than passive cooling could manage. Engineers installed a mechanical cryocooler, a device that pumps helium gas through a cycle of compression and expansion, each cycle pulling a tiny bit more heat away from the detector. The system works like a refrigerator the size of a suitcase, running continuously in deep space, chilling one small detector to temperatures that do not exist naturally anywhere on Earth. This engineering feat nearly derailed the entire mission. The cryocooler went through years of redesign. Early versions failed testing. The system had to work flawlessly in a vacuum, with no maintenance possible, for a planned mission lifetime of 10 years. One malfunction and the most sensitive eye humanity ever pointed at the sky goes permanently dark. The cryocooler passed its final tests. It launched. It works. And the data coming from those near-zero sensors has already rewritten parts of astronomy that scientists thought were settled. But keeping the telescope cold requires keeping it away from heat. And the biggest sources of heat in our solar system are the sun, obviously, and surprisingly, the inner planets. Earth glows in infrared. Venus radiates enormous heat. Mercury sits so close to the sun, it is essentially a furnace. Webb cannot look at any of them. The telescope's targeting system includes a permanent exclusion zone around the Sun, Earth, Moon, Mercury, and Venus. Point the mirror toward any of those, and the sun shield would have to tilt. Heat would pour in, the instruments would warm, and a $10 billion telescope would become an extremely expensive piece of dead metal. This is why Webb's 1 million mile journey mattered. Distance is protection, and the place Webb parks itself is stranger than most people realize. 1 million miles sounds like a random number. It is the exact opposite. Webb sits at a location called the second Lagrange point, named after the mathematician who calculated where it sits. At this specific spot in space, the gravitational pull of the Earth and the gravitational pull of the Sun balance each other in a way that lets a spacecraft orbit the Sun at the same rate Earth does. Webb stays locked in place relative to Earth, always 1 million miles directly behind the planet, always in Earth's shadow. This is critical for two reasons. First, Webb needs to keep the Sun, Earth, and Moon all on the same side of its sun shield at all times. At the Lagrange point, that is possible. The three heat sources cluster together from Webb's perspective, all blocked by one shield. The cold side of the telescope always faces deep space, always facing backward into the ancient dark. Second, staying in sync with Earth's orbit means communication is straightforward. Webb's data does not have to chase a moving planet. It always knows exactly where Earth is. Ground teams can send commands and receive data on a predictable schedule. The journey to reach this spot took about 30 days after launch. Webb traveled 1 million miles through deep space, while engineers watched anxiously. The telescope had to unfold itself during that journey. First, the sun shield, 5 layers of a material similar to aluminum-coated Kapton film, each layer thinner than a human hair and the size of a tennis court. Then the secondary mirror, mounted on 3 long arms extending forward from the main body. Then the main mirror segments folding out like the petals of a metallic flower. 297 individual mechanisms had to operate perfectly. Every motor, every hinge, every latch, a single failure in any of them would have ended the mission. Scientists describe this period as terror. 30 days of unfolding in a place too far for any repair mission, with no way to know for certain if each step succeeded until telemetry arrived from 1 million miles away. Every mechanism worked. Webb arrived at the Lagrange point, locked into its orbit, and the cold side of the mirror began its long drop toward absolute zero. The exclusion zone around the inner solar system is permanent. Webb will never look at Earth. It will never photograph our moon. It cannot image Venus, Mercury, or the surface details of Mars up close without risking damage. The telescope was built to stare outward, into the deep past, into the cold and the dark. And in that cold and dark, something waited, the earliest period of the universe. The era before galaxies existed as we know them. The era before stars had lived and died enough times to build the heavy elements that make up planets and people. The era when the universe was a sea of hot gas, slowly pulling itself together under gravity for the very first time. Scientists call it the cosmic dawn. And for most of human history, it was completely invisible. No telescope could reach it. Webb reached it. What it found there was stranger than the scientists who built the telescope expected, and they had spent 30 years expecting the extraordinary. Before galaxies, before stars, before planets, the universe was dark. Scientists call this the cosmic dark ages. After the Big Bang, the universe cooled. Hydrogen gas spread across space in enormous clouds. For roughly 200 million years, nothing glowed. Nothing lit the dark. Space was a cold, expanding fog with no sources of light anywhere. Then gravity went to work. Gas clouds began to collapse under their own weight. As they collapsed, they heated up. The densest pockets grew hot enough to trigger nuclear fusion. Hydrogen atoms began fusing into helium, releasing energy. Releasing light, the first stars switched on. This moment is the cosmic dawn. Scientists confirmed it happened somewhere between 150 million and 350 million years after the Big Bang. The exact timing remains uncertain. The exact locations of those first lights are unknown, but the event itself is confirmed through multiple lines of evidence. Those first stars were nothing like the sun. They were enormous, hundreds of times more massive than our star. They burned at temperatures that made them blaze blue-white, so hot they would make the sun look dim by comparison. And because of their enormous mass, they burned through their fuel fast. They lived for only a few million years, then exploded as supernovas, scattering the heavy elements they had forged inside their cores. Those explosions seeded the surrounding gas with the first carbon, oxygen, nitrogen, and iron that had ever existed in the universe. The next generation of stars formed from that enriched gas, and inside those second generation stars, heavier and heavier elements built up. Eventually, some of those stars formed with rocky planets. On at least one of those planets, the atoms forged in the first stars eventually assembled into living things. Every atom heavier than hydrogen in your body came from a star. But humans could never observe the cosmic dawn directly, because the light from that era is ancient, stretched, faint, and buried behind billions of light years of expanding space. Even the Hubble Space Telescope, one of the greatest scientific instruments ever built, could only see galaxies that formed roughly 800 million years after the Big Bang. The cosmic dawn sat hidden behind a wall Hubble could not cross. Webb crossed it. Using its infrared sensors and its massive cold mirror, the telescope began detecting galaxies from the very edge of the dawn. Galaxies that formed just a few 100 million years after the Big Bang. Baby galaxies. Galaxies so young they had barely begun building their first generations of stars. And when scientists looked at these galaxies carefully, something felt wrong. The galaxies were too bright, too massive, too chemically complex. They carried signatures of elements that should have taken far longer to appear. Standard models of how galaxies form predicted smaller, dimmer, simpler structures at this age. Webb kept finding the opposite. The models were built over decades. They were tested carefully. Scientists trusted them. Webb started breaking them one by one. The first major crack appeared in the data from a galaxy so distant its light took 13.4 billion years to arrive. A galaxy called JDS-GS Zone 3, 0. And its discovery did not happen the way most people imagine. It happened during one of the most ambitious observation programs the telescope has ever run. Every galaxy in the universe is moving away from us. All of them, in every direction, at speeds that increase with distance. The farther a galaxy sits, the faster it recedes. This is the expansion of the universe, and it leaves a fingerprint on every photon that crosses the cosmos. That fingerprint is redshift. Light travels as waves. Like ripples on water, those waves have a specific length from peak to peak. Visible light comes in a range of wavelengths. Short wavelengths appear blue, long wavelengths appear red. When a galaxy moves away from us, the light waves it emits get stretched during the journey. The wavelengths grow longer. The color shifts toward red. The more a galaxy has moved away during the time its light was traveling, the more that light stretches. And because the universe has been expanding continuously since the Big Bang, the oldest, most distant light has been stretching for the longest time. The light from the earliest galaxies has stretched so far it moved completely beyond the red end of the visible spectrum. It pushed into infrared. Scientists measure redshift with a number. A galaxy with a redshift of 1 has had its light wavelength doubled during transit. A galaxy with a redshift of 5 has had its light stretched 6 times its original wavelength. A galaxy with a redshift of 13 has had its light stretched to 14 times its original size. Redshift 13 sits at the very edge of what any instrument has ever confirmed. To confirm a redshift value, scientists use a tool called a spectrograph. It splits incoming light into a spectrum, the way a prism breaks white light into a rainbow. Every chemical element absorbs and emits light at specific wavelengths, producing a unique pattern of lines in that spectrum. Scientists recognize those patterns and use them to identify the elements present in a galaxy. When a galaxy has high redshift, those patterns shift toward longer wavelengths. By measuring how far the patterns have shifted, scientists calculate the exact redshift value. The calculation gives both the distance and the age of the light. Webb's spectrograph is the most sensitive ever launched. It can split light from galaxies so faint they would be completely invisible to any prior instrument. It can confirm redshift values that Hubble could only estimate. And in late 2022, it confirmed something remarkable. A team of astronomers had flagged a tiny red dot in Webb's early images. The dot showed up in infrared bands. It was absent in shorter wavelengths. That pattern suggested a galaxy with extreme redshift, a galaxy so distant that all its visible light had stretched beyond detection, leaving only infrared behind. The spectrograph confirmed it. Redshift 13.2. The light from this galaxy left its source 13.4 billion years ago. The universe was only 320 million years old at that moment. The Big Bang had happened a little over 300 million years earlier. This galaxy was alive when the universe was barely out of its infancy. The number that followed the confirmation hit scientists like a cold wave. Because of the universe's expansion during those 13.4 billion years of travel time, that galaxy now sits 33 billion light years away from Earth. The light that finally arrived at Webb's mirror started its journey from a place that is now 33 billion light years distant. That number breaks common sense. And the reason it does opens a door into something even harder to wrap your mind around. September 29th, 2022, a team of astronomers studying Webb's early data spotted something in an image that stopped them cold. A dot. A red dot so small it barely registered as a distinct object. No spiral arms, no visible structure. Just a faint smear of light in a corner of an image packed with thousands of other galaxies. They flagged it, the spectrograph locked on, it split that ancient light into its component wavelengths. The chemical fingerprints shifted so far toward infrared that the pattern matched a redshift of 13.2. Confirmed. Spectroscopically verified. The most distant galaxy humanity had ever pinned down with certainty. Scientists named it Jade SGS Zone 3, 0. The name comes from the survey program, the field location, and the redshift value. For the purposes of this story, call it the 13.2 galaxy. Its light left home 13.4 billion years ago. At that moment, the universe was only 320 million years old. To give that perspective, our solar system is 4.6 billion years old. The light from this galaxy departed before our sun existed, before Earth existed, before the molecular cloud that would eventually collapse into our solar system had even begun to gather. That light crossed an almost incomprehensible distance over those billions of years. It dodged or passed through galaxy clusters. It stretched as the universe expanded around it. It shifted from visible wavelengths all the way into the infrared, and it finally landed on Webb's gold mirror, 1 million miles from Earth. The scientists who confirmed the redshift called colleagues. Emails went out, the numbers circulated through the astronomy community before the paper was formally published. The reaction was something between excitement and unease. Excitement because this was exactly the kind of discovery Webb was built to make. Unease because the galaxy at that redshift was larger and more developed than standard models predicted. A galaxy 320 million years old should be young, small, simple. A loose collection of early stars, still forming, still chaotic. The 13.2 galaxy showed signs of structure. Stars had already been forming for some time. The chemical content of its light suggested generations of stellar activity. Something had been going on inside it for longer than the models said was possible. Scientists did not panic. Anomalies in new data are common. Instruments need calibration. Models need adjustment. Single data points do not overturn decades of work. But then more galaxies came in, more early candidates, more objects at extreme redshift that showed the same pattern. Too developed, too bright, too chemically complex for their age. The 13.2 galaxy was an early warning sign. A signal that something about the standard picture of how the universe evolved was missing a piece. And then a second galaxy arrived, one even older. One that shattered the record held by the 13.2 galaxy and raised questions that are still open today. But before that story, consider the number once more. 33 billion light years away, the light traveled for 13.4 billion years, but the galaxy now sits 33 billion light years from Earth. How can light that traveled for 13.4 billion years have come from a place that is 33 billion light years away? The answer changes how you think about the universe permanently. 13.4 billion years of travel time, 33 billion light years of current distance. Those two numbers seem to contradict each other. If light traveled for 13.4 billion years, should the source be 13.4 billion light years away? Common sense says yes. But common sense was not built for an expanding universe. Here is the key. Space itself expands. Every point in space is moving away from every other point. Galaxies are not flying through space like rockets. Space is stretching between them like dots on a balloon being inflated. The dots do not move across the balloon's surface. The surface itself grows, and the dots ride it apart. When the 13.2 galaxy emitted that ancient light, it sat perhaps 30 million light years from the patch of space that would eventually become our solar system. Both regions were close. As cosmic distances go, the universe was young and compact. But as that light traveled toward us over 13.4 billion years, the space it was crossing kept expanding. The galaxy kept moving away, carried by that expansion. The distance between us and the galaxy grew continuously during the entire journey. By the time the light arrived at Webb's mirror, the galaxy had been carried to a position 33 billion light years away. This is confirmed physics. It follows directly from the equations of general relativity and the observed expansion rate of the universe. Scientists call the current distance to a distant object its proper distance, to distinguish it from how far its light actually traveled. The edge of the observable universe, the farthest point from which any light has had time to reach us, sits about 46 billion light years away. The universe is only about 13.8 billion years old. Those two numbers seem to conflict for the same reason. Space expanded during the journey. Webb is seeing objects that are currently somewhere between 30 and 46 billion light years from Earth. Objects whose light spent billions of years crossing a universe that was simultaneously growing in every direction beneath that light. This creates a strange consequence. Somewhere beyond the observable edge, there are galaxies that will never be visible to us. They exist right now. Their light is heading toward us, but the universe is expanding so fast that the space between us and those galaxies grows faster than light can cross it. That light will never arrive. We will never see those galaxies. Ever. The universe contains regions forever hidden behind a horizon that has nothing to do with walls or barriers, just expansion, outrunning light itself. This also means the universe we can observe is a bubble defined by time and light speed, surrounded by an infinite dark we will never access. Webb is pushing to the very edge of that bubble, catching the last photons that squeezed inside before the expansion locked them out. And inside that bubble, astronomers recently finished the largest map of galaxies ever created, a map that revealed something about the structure of the universe that most people have never seen. Zoom into the image, find the tiny red dot. It looks like nothing. A smudge, a pixel, something a photo editor might clean up by accident. But inside that smudge, billions of stars are burning. Billions. Active, massive, radiating energy into the darkness in every direction. Early galaxies do not look like the galaxies in science textbooks. The textbook galaxy is the Milky Way or Andromeda, sweeping spiral arms, a bright central bulge, lanes of dust and gas catching starlight, beautiful and enormous. Early galaxies look like dots. The reason is distance. 13 billion light years of travel time compresses the image of even a vast galaxy into something smaller than a single pixel in a standard camera. Webb's sensors are extraordinarily sensitive, but the physical limit of angular resolution, how small a detail the telescope can distinguish, means that the most distant galaxies appear as featureless smears of light. But the light itself carries information. The spectrograph does not care what shape a galaxy looks like. It reads the chemistry, it reads the redshift, it reads the energy output. From that information, scientists calculate the mass of stars inside the galaxy, the rate at which new stars are forming, and the chemical history of the gas those stars formed from. And those calculations revealed something surprising. The earliest galaxies were forming stars at an astonishing rate. A galaxy that should still be in its infancy, building its first few clusters of stars, was instead producing new stars at a pace that rivaled the star formation rates of much larger, much older galaxies. One galaxy from this era was forming stars at a rate equivalent to producing several hundred copies of our Sun every single year. Our Milky Way currently produces about 1 to 3 new stars per year. These early galaxies were factories running at maximum capacity. The energy output from all that star formation is why they are detectable at all. Those billions of blazing young stars pour out radiation that stretches across billions of light years and still arrives at Webb's mirror with enough energy to register. The tiny red dot is alive, furiously alive, and the dots keep appearing in every direction Webb points, in every deep field image. Thousands of early galaxies, all showing the same pattern of aggressive early star formation that current models struggle to explain. Each dot is a question mark. Scientists had a framework for how galaxies should evolve. It was built from decades of observation with prior telescopes, refined with computer simulations, tested against the data available before Webb launched. The framework worked reasonably well for the galaxies those telescopes could see. Webb sees farther, and the framework starts to crack at the edges. The clearest sign of that crack came when astronomers pointed the telescope at a patch of sky and ran the largest deep field observation program in Webb's history, a program designed to map the architecture of the universe at a scale nobody had attempted before. The result was 164,000 galaxies stitched into a single image, and it showed the universe organizing itself into patterns that are stranger and larger than anyone predicted. July 11th, 2022. The White House. The President of the United States walked to a podium and unveiled an image on a screen behind him. It was called the First Deep Field, a small patch of sky, carefully selected, observed by Webb for about 12.5 hours. The image showed thousands of galaxies, spiral galaxies, elliptical galaxies, distorted galaxies stretched into arcs by the gravity of closer galaxy clusters, bending their light. Galaxies behind galaxies behind galaxies, layered into the depth of the image, like lights in a dark room seen through a rainy window. The patch of sky that produced this image is tiny, smaller than a grain of sand held at arm's length from your face, and it contained more galaxies than astronomers expected. Far more. Scientists who had spent years designing the observation were not entirely surprised. They knew Webb was powerful, but seeing the raw image hit differently than running the numbers, one researcher described the experience as opening a door and finding a new room behind it, except the room was infinite. Hubble had taken similar deep field images. The most famous, the Hubble Ultra Deep Field, revealed about 10,000 galaxies in a similar patch of sky and required 11 days of observation. Webb produced a comparably rich image in 12.5 hours. The sheer efficiency meant that Webb could survey far more sky in its operational lifetime than Hubble could. Every hour of Webb observation time produced data that would have required days from its predecessor. The image circulated worldwide within hours. Social media filled with zoomed-in versions, people highlighting individual galaxies, pointing at the arcs of bent light, asking questions about what each smear of color represented. The public engagement with a single astronomical image was unlike anything since the original Hubble Deep Fields. But the scientific reaction behind the scenes was more complicated. The image was stunning, and the data inside it was immediately strange. The galaxies at the farthest distances in that image showed the same pattern Webb kept finding everywhere it looked. Stars forming faster than expected. Chemical signatures more complex than their age should allow. Structures more organized than models predicted for that era. The first deep field image was a preview, a teaser of what was coming. A signal that the universe at its earliest stages was doing something the standard model of cosmic evolution had not predicted. Astronomers started calling each other. Papers began circulating. Phrases like tension with the standard model and Unexpected results appeared in draft manuscripts circulating before peer review, and all of this came from a single 12-hour observation of a grain of sand's worth of sky. Webb had decades of observation time ahead of it. It had the entire sky to examine. The early galaxies were the first mystery, but the structure those galaxies built over billions of years was the next one. And that structure turned out to be one of the largest and most complex things in existence. Galaxies do not float randomly, scatter a handful of sand across a floor, and the grains fall wherever gravity and luck place them. But galaxies followed a different pattern as the universe evolved. They organized, they gathered, they connected into a structure so vast, it has no human equivalent. Scientists call it the cosmic web. Picture a three-dimensional spider web the size of the observable universe. The threads of that web are filaments, long chains of gas, and dark matter stretching for hundreds of millions of light years. Along those threads, galaxies cluster like dewdrops on the strands of a real web. Where threads intersect, enormous galaxy clusters pile up, containing thousands of galaxies packed into a region of space. Between the threads sit voids, empty spaces dozens or hundreds of millions of light years across, containing almost nothing. No galaxies, minimal gas, just dark space. The cosmic web is the largest structure in the universe. It fills everything. Every galaxy we know, including our own Milky Way, sits somewhere on a filament or at a junction of this web. Our galaxy cluster, called the local group, sits near the edge of a larger structure called the Virgo supercluster, which itself is part of an even larger supercluster called Laniakea, about 520 million light-years across. Scientists had theorized that the cosmic web existed long before they could see it directly. The math of how gravity, dark matter, and dark energy interact over billions of years predicted that matter would not spread evenly through space. It would collapse along preferred directions, forming filaments and voids. Simulations confirmed the prediction. But simulations are models. Seeing the actual web required observations powerful enough to map real galaxies across enormous distances. Webb is providing that data, and the latest maps are showing a web that matches the simulations in general structure, but differs in the details. The filaments in the real universe are denser in some regions. The voids are deeper. The early web, from the first few billion years of cosmic history, shows structure that assembled faster than the models suggested it should. Something caused matter to organize more quickly in the early universe than current physics predicts. That something is probably tied to dark matter, the invisible substance that makes up about 27% of everything in the universe. Dark matter does not interact with light. It cannot be seen directly, but its gravity shapes how ordinary matter moves. And in the early universe, dark matter halos formed first, pulling ordinary gas into the filaments that would eventually become the cosmic web. The exact properties of dark matter remain unknown. Scientists know it exists through its gravitational effects. They know it outweighs ordinary matter by a factor of 5 to 1, but they have never detected a single dark matter particle directly. And every time a new telescope maps the cosmic web with more detail, new questions about dark matter surface. The next attempt at mapping this web was the most ambitious project Webb has ever run, and it produced a catalogue that changed the scale of what astronomers consider possible. 255 hours. That is how long the James Webb Space Telescope stared at a single region of sky to build the most detailed map of the early universe ever created. The project is called Cosmos Webb. It is the largest observation program the telescope has run since its launch. The team wanted to capture the cosmic web across a wide area of sky, tracking how galaxies cluster and connect across different distances and different eras of cosmic history. The patch of sky they chose covers an area roughly equivalent to the width of 3 full moons placed side by side. In astronomy terms, that is enormous for a deep field survey. Most deep field images cover a tiny fraction of that area. Covering this much sky with Webb's sensitivity required an enormous investment of observation time, which is why the program demanded 255 hours. To build the final image, the team stitched together more than 10,000 separate exposures. Each exposure captured a slightly different region or a slightly different wavelength of light. Combining them required months of computer processing and careful calibration. The result was a catalogue of 164,000 individual galaxies, 164,000 galaxies, each one a separate island of billions of stars, each one with a measured distance, a measured brightness, a measured chemical profile, and a position in three-dimensional space. This catalogue covers galaxies across a wide range of cosmic history, from galaxies relatively nearby to galaxies from the first few billion years of the universe. By plotting all of them in 3 dimensions, astronomers can watch the cosmic web evolve across time. Early epochs show the web forming, filaments thickening, voids deepening. Later epochs show the mature web we see today. The data from this survey will take years to fully analyze. Scientists are currently sifting through it, publishing papers on specific subsets of galaxies, specific filaments, specific voids that show unexpected properties. One early result stood out immediately. The cosmic web in the early universe assembled faster than the standard model predicted. Galaxy clusters appeared at redshifts where the models expected isolated small galaxies just beginning to interact. The web showed organization at an epoch when, according to standard theory, organization should still have been forming. This matched what Webb was finding everywhere it pointed. The early universe was ahead of schedule. One of the most striking entries in the Cosmos Web catalog was a galaxy cluster from the cosmic dawn that showed the kind of gravitational organization normally associated with much older structures. A cluster of galaxies clumped together so tightly and so early that scientists compared it to finding a fully grown tree in a pot where you just planted the seed. And the organization visible in that cluster pointed directly toward the largest single structures in the catalog, megastructures, walls of galaxies and voids stretching across hundreds of millions of light years. What those structures look like, and why they exist at all, broke open an entirely new set of questions. Stand in the middle of a field and look out in every direction. You see flat ground, but zoom out to a satellite view and the landscape reveals hills, valleys, rivers, and ridges invisible from the ground. The structure only appears at the right scale. The cosmic web works the same way. From inside a galaxy, the universe looks mostly empty. Zoom out to hundreds of millions of light years, and the web appears. Filaments, walls, voids. A foam-like structure of matter surrounding enormous bubbles of almost nothing. The voids are the strangest part. A cosmic void is not just empty space between galaxies. It is a region of space where the density of matter dropped so low, so early in cosmic history, that gravity never managed to pull things together. While the filaments and walls accumulated matter over billions of years, the voids kept losing it, matter draining away toward the filaments along the edges, leaving the interior increasingly bare. The largest known void in the observable universe is called the Boötes void. It stretches about 330 million light-years across. If our Milky Way sat in the center of the Boötes void, our nearest neighboring galaxy, the Andromeda Galaxy, about 2.5 million light-years away, would still be inside the void with us. We would not be able to see another galaxy until we had traveled over 150 million light-years in any direction. The Cosmos Web survey found similar structures in the early universe. Voids forming at epochs when the standard model predicts the universe should still be relatively smooth, before large-scale structure had time to sharpen into clear voids and walls. The walls are equally striking. A galaxy wall is a flat sheet of galaxy clusters extending for hundreds of millions of light-years. From inside the cosmic web, a wall looks like a thin plane of bright spots, galaxies lining up along a boundary between a void and a filament. The largest known wall in the observable universe, called the Hercules Corona Borealis Great Wall, stretches about 10 billion light-years across. Confirmed. That structure is so enormous, it covers a significant fraction of the entire observable universe. Structures this large present a problem for standard cosmology. The models predict that the universe should be roughly uniform at scales above 1 billion light-years. Matter should average out. The web should stop showing organized patterns, at that scale. Large structures beyond a certain size should be statistically impossible given the age of the universe and the rate at which gravity acts. But they exist, and Webb's deep surveys keep finding hints that organized structure appeared earlier and on larger scales than the models allow. Each new map of the cosmic web adds another data point to a growing list of anomalies that do not fit the standard picture neatly. The most extreme anomaly Webb found sits inside one of the oldest galaxies in the catalogue. A galaxy so ancient and so chemically strange that its chemistry is forcing scientists to question not just how galaxies form, but how the first elements in the universe were made. That galaxy is month over month Z14, and its discovery earlier this year changed the record books. January 26th, 2026, a paper dropped in the scientific community. A team of astronomers announced the confirmation of a galaxy with a redshift of 14.4, light that left its source 280 million years after the Big Bang. The galaxy carries the name month over month, Z14. Scientists studying it immediately called it month over month, the first part of the catalogue name. For this story, that name works fine, 280 million years. Pause on that number. Our solar system is 4.6 billion years old. 4,600 million years, month over month, formed when the universe was 280 million years old. To compare those numbers, if the entire history of the universe were compressed into a single year, month over month formed before January 8th. This shattered the previous record. The 13.2 galaxy had held the confirmed distance record since 2022. Month over month pushed past it with a higher redshift confirmed through spectroscopy, the rigorous method that measures chemical fingerprints in the light rather than guessing from the color pattern alone. Spectroscopic confirmation matters because early candidates often turn out to be closer galaxies misidentified by their colors. The spectrograph removes the ambiguity. When month-over-month spectrum came back confirming redshift 14.4, the scientific community accepted it. Month-over-month is currently the oldest confirmed galaxy in existence. The light that reached Webb's mirror left this galaxy before any star in our solar system existed. Before the Earth existed, before the gas cloud that would become our sun had even begun to collapse. The galaxy's light traveled for 13.5 billion years to arrive at Webb. What makes month over month particularly strange is its size and chemical content. A galaxy 280 million years into cosmic history should be compact, sparse, and chemically simple. Mostly hydrogen, some helium, almost nothing else. Month over month showed something different. Its spectrum contained signatures of heavier elements, nitrogen, carbon, elements that stars have to forge across multiple generations, elements that require stars to live, die, and explode, scattering their cores into the surrounding gas before the next generation of stars forms from that enriched material. For month over month to show these signatures at 280 million years, the universe had to have produced and recycled multiple stellar generations in an impossibly short time. Stars that formed in the first 100 million years would need to have lived, died, enriched the gas, and allowed new stars to form, all before month over month's light left it at 280 million years. Scientists confirm that the nitrogen signature is real. They confirm the data. What they cannot confirm is how month over month produced it so fast. That mystery connects to something even stranger, because the same chemical fingerprint that appears in month over month appears somewhere else entirely, somewhere much closer to home, somewhere inside our own galaxy. The standard model of galaxy formation has rules. Galaxies grow from small seeds. Early in cosmic history, dark matter halos formed first, invisible gravitational wells that pull ordinary gas inward. That gas cools, collapses, and begins forming stars. Over hundreds of millions of years, the galaxy grows, star by star, merger by merger, slowly building mass and complexity. The earliest galaxies should reflect this gradual process. Small, low mass, simple chemistry, just beginning to produce the first generations of stars. This prediction held up through decades of observations with every telescope available before Webb launched. Webb found month over month a galaxy 280 million years old, with more mass than the model allows, more chemical complexity than the timeline permits, and a star formation rate that suggests it had already been running at high capacity for long enough to produce multiple stellar generations. This is a confirmed problem, not a theory. The data from the spectrograph is solid. The mass estimates carry uncertainty, but sit consistently above what models predict. The nitrogen and other heavy element signatures are real. Scientists have offered several possible explanations. One possibility is that the very first stars, the ones from the cosmic dark ages before month-over-month era, were even more massive and shorter lived than current estimates. If the first generation of stars burned through their fuel in just a few million, they could have lived, died, and enriched the surrounding gas in time for month-over-month stars to form from that material. Another possibility involves black holes. Supermassive black holes at the centers of early galaxies could have released enormous amounts of energy as they consumed surrounding gas, heating and compressing nearby material into stars far faster than normal processes would allow. Webb has already found evidence of supermassive black holes in very early galaxies, black holes far larger than the models expect at those ages. A third possibility is more unsettling. The initial conditions of the universe immediately after the Big Bang may have produced density variations different from what the standard model assumes. If some regions of the early universe were denser than expected, gravity could have assembled massive galaxies far faster in those regions. All three explanations remain active theories. None of them alone closes the gap fully. The honest answer from the scientific community is that month-over-month's existence is a real challenge to the model, and the model likely needs revision. How significant a revision? That depends on a chemical mystery hiding inside month-over-month spectrum, a specific element that appears in quantities that no current process explains well. That element is nitrogen, and its presence in month-over-month points directly to a secret hiding inside the oldest stars in our own galaxy. Pick up any object near you right now. The nitrogen inside it, in the air, in the materials, in your own body, was made inside a star. That nitrogen was forged when a massive star, late in its life, began fusing heavier and heavier elements in layers, like an onion, burning carbon and oxygen in shells around its core until the core collapsed. That process takes time. Stars massive enough to produce nitrogen live for millions of years before dying. Then their debris must cool, spread through the surrounding gas, and eventually be swept up by the next generation of stars forming from that enriched material. Astronomers estimate this cycle takes hundreds of millions of years at minimum, often longer. Month over month completed this cycle before it was 280 million years old. The nitrogen in month-over-month spectrum was identified through specific spectral lines. Confirmed signatures of ionized nitrogen glowing in the light from the galaxy's most active star-forming regions. The abundance, meaning the concentration of nitrogen relative to other elements, sits significantly higher than models of early galaxy chemistry predict. This is called the nitrogen anomaly. Scientists confirm it appears in multiple early galaxies observed by Webb. Month over month shows it clearly. Other high redshift galaxies show similar enrichment patterns. The anomaly is real and consistent. Researchers studying it notice something striking. The nitrogen enrichment pattern in these ancient galaxies closely resembles a pattern found in a different location entirely. The oldest stars inside our own Milky Way, stars called Population 2 stars, show a similar chemical profile. Population 2 stars are the most ancient stars still burning in our galaxy today. They formed in the earliest epochs of the Milky Way's history, from gas already enriched by the first stellar generation that came before them. Some of these stars sit in globular clusters, dense spherical groups of hundreds of thousands of stars orbiting the outer halo of our galaxy. The chemical similarity between month-over-month spectrum and the composition of our galaxy's oldest stars suggests a direct connection. The first stellar generation that enriched month over month may have been the same type of extremely massive, short-lived stars that seeded the early Milky Way. Stars that burned so hot, so fast, and so furiously that they compressed the stellar evolution timeline in ways current models have not fully captured. If that is correct, the atoms inside the oldest stars in our own galaxy carry a chemical signature from the same cosmic event visible in a galaxy 13.5 billion light-years away. You and that ancient light share a common origin. The first stars that died to build the elements in month over month also died to build the elements in our galaxy, in the sun, in Earth, in every living thing, but the nitrogen anomaly is a chemical mystery. The next problem Webb is forcing scientists to confront is a mathematical one, a disagreement between two different ways of measuring the universe that has been simmering for years and that Webb has now made impossible to ignore. Scientists call it the Hubble tension, and it suggests that either our measurements are wrong or our understanding of the universe at the most fundamental level is incomplete. The Milky Way is ancient. Most people know that, but few people realize just how old the oldest parts of it actually are. Scattered across the outer halo of our galaxy, far above and below the flat spiral disk where our sun lives, sit dense spherical clusters of stars. Each cluster contains hundreds of thousands of stars packed into a ball only a few hundred light-years across. These are called globular clusters. Our galaxy has about 150 of them, orbiting like slow satellites. The stars inside the oldest globular clusters formed when the Milky Way itself was young. Some of them are 13 billion years old, nearly as old as the universe. They formed from the first enriched gas available in our region of the cosmos, gas that had already been processed through at least one generation of massive, short-lived stars before them. Scientists call these ancient survivors population 2 stars. When astronomers analyze the chemical composition of population 2 stars, they build a spectrum, a chemical fingerprint, lines corresponding to hydrogen, helium, carbon, oxygen. The ratios between these elements tell the story of what the gas those stars formed from looked like before they ignited. In 2022 and 2023, as Webb data on early galaxies began accumulating, a team compared the nitrogen enrichment patterns in those ancient galaxies with the nitrogen patterns inside population 2 stars. The match was striking. The same overabundance of nitrogen relative to oxygen and carbon that appeared in month over month and in other early high redshift galaxies also appeared in the chemical fingerprints of the oldest stars, orbiting our own galaxy. The pattern was not identical across every sample, but the similarity was consistent enough that multiple independent research groups flagged it. This matters enormously. The oldest stars in our galaxy formed from gas that was chemically similar to the gas-forming stars in the most distant galaxies Webb can see. The first stellar generation that died and scattered heavy elements across the early universe seeded both regions. The early Milky Way and the galaxy we call month over month drew from the same cosmic chemistry set. The atoms in a population 2 star in a globular cluster 30,000 light-years from Earth share a chemical origin with atoms in a galaxy 13.5 billion light-years away. The connection runs even deeper. Some researchers suggest that globular clusters themselves may be the surviving cause of early dwarf galaxies that merged into the Milky Way billions of years ago. If that is correct, the globular clusters orbiting our galaxy today are remnants of structures similar to the tiny early galaxies Webb observes at extreme redshift. Ancient fragments preserved inside a larger galaxy carrying the chemical memory of the universe's first stellar generation. The Milky Way may contain living fossils of the cosmic dawn. Scientists describe this connection as a thread linking the edge of the observable universe to the stars visible on a clear night above your head. The chemistry is real. The link is confirmed in pattern, if not yet fully explained in mechanism. And while this chemical mystery plays out across cosmic history, a completely separate problem has been building inside the equations astronomers use to describe the universe's expansion. A problem so stubborn that Webb was specifically tasked with helping to solve it. A problem that, even after Webb's data came in, refused to go away. the universe is expanding. Scientists confirmed that nearly a century ago, but how fast, that question has a number attached to it. Scientists call it the Hubble constant. It measures how quickly galaxies move away from each other as space stretches. A higher number means faster expansion. A lower number means slower expansion. To measure it, astronomers use two completely independent methods, and the two methods disagree. The first method looks at the nearby universe. Scientists measure the distances to variable stars, a special type of star that pulses in brightness, at a rate tied to its actual luminosity. By comparing how bright those stars look from Earth versus how bright they actually are, astronomers calculate precise distances. Combine distance measurements with speed measurements from redshift, and you get an expansion rate. This method consistently returns a value near 73 kilometers per second per megaparsec, which essentially means that for every 3.3 million light years of distance between 2 points, those 2 points are moving apart at 73 kilometers per second. The second method looks at the ancient universe. It analyzes the cosmic microwave background, the faint glow of heat left over from the Big Bang itself, detectable in every direction across the sky. By studying the pattern of temperature variations in that ancient glow, scientists calculate what the expansion rate should be based on the physics of the early universe. This method consistently returns a value near 67 kilometers per second per megaparsec. 73 versus 67. That gap sounds small. For cosmologists, it is enormous. Both measurements have been refined for decades. Both have been cross-checked by multiple independent teams using different instruments and different datasets. The gap has not closed. If anything, each round of refinement has confirmed the discrepancy more solidly. Scientists call this the Hubble tension. It is one of the biggest unsolved problems in modern physics. There are three possible explanations, and none of them is comfortable. First, one or both measurement methods contains a systematic error that nobody has identified yet. An unknown flaw in how scientists calibrate variable stars, or a subtle misunderstanding of the early universe's physics that skews the microwave background calculation. Second, the laws of physics operated differently in the early universe compared to today. Something changed. Dark energy, the force driving the expansion, may have varied in strength over cosmic history in ways the standard model does not account for. Third, the standard model of cosmology is fundamentally incomplete. The Big Bang framework, with its assumptions about dark matter, dark energy, and the initial conditions of the universe, may be missing a component that would reconcile the two measurements. Each option carries major consequences, and then Webb got involved. In 2023, Webb teamed up with the Hubble Space Telescope on a specific mission. The goal was to check the first measurement method from the ground up. Variable stars had been the foundation of the nearby expansion rate calculation for decades. Hubble measured them for years. But Hubble operates in visible light, and some researchers worried that crowding inside distant star clusters made individual stars hard to isolate cleanly. Maybe light from neighboring stars was contaminating the measurements and inflating the result. Webb's infrared vision cuts through that problem. In infrared, the contrast between individual stars inside a dense cluster is sharper. Crowding effects that plague visible light measurements shrink considerably. If the variable star measurements were contaminated by crowding, Webb would show it. The team ran the analysis. They compared Hubble's measurements of the same variable stars with Webb's independent infrared measurements of the same stars. The results matched Hubble's numbers. The variable stars gave the same expansion rate in infrared as they did in visible light. The crowding concern was real, but its effect on the final measurement was too small to explain the gap. The Hubble tension survived. Confirmed. The discrepancy between the two measurement methods is real and cannot be explained by instrument error or crowding effects in the variable star data. This result was significant enough that the team published it in a major journal, and the broader physics community paid attention. Two independent telescopes using two different wavelength ranges measuring the same stars and arriving at the same number. The measurement is solid, which means the problem is real. The universe is expanding faster than the Big Bang model predicts it should be. Either the model is missing something, or the physics of dark energy is more complex than the standard equations capture, or something changed in the universe's expansion history that left a permanent imprint on the current rate. Scientists immediately started proposing modifications to the standard model. Early dark energy is one candidate, a form of dark energy that existed in the early universe and then faded, boosting the expansion rate early and leaving the current rate elevated. Interacting dark matter is another, a scenario where dark matter particles interact with each other in ways that alter the expansion rate over time. None of these proposals have been confirmed. All of them require changes to the standard model, a model that has successfully described the universe's large-scale behavior for decades. The Hubble tension does not mean the Big Bang model is wrong. It means the model is incomplete. Something is missing from our understanding of what drives the universe's expansion, and that missing piece might be connected to the most mysterious substance in existence. Something that makes up 68% of everything in the universe, drives its acceleration, and has never been directly detected or explained. Imagine building a bridge using two different sets of measurements. One team measures from the east side, the other measures from the west. When they meet in the middle, the two halves do not align. The gap between them is not large enough to see from a distance, but up close, the mismatch is undeniable. That is the situation astronomers face with the universe's expansion rate. Two methods, two results. A gap that refuses to close. For most scientific disputes, a gap like this eventually resolves through better measurements. A flaw surfaces. A calibration error appears. One method turns out to carry a hidden bias. Scientists correct it, the numbers converge, and the field moves forward. Webb ruled out the most obvious candidate for that hidden bias. The variable star measurements stand. The gap is real. That forces the scientific community to consider what it means if the physics is genuinely different from what the standard model predicts. The standard model of cosmology, sometimes called the lambda CDM model, is built on a set of assumptions about the composition of the universe and the behavior of dark energy over time. Lambda refers to the cosmological constant, Einstein's term for the energy of empty space, the force driving the universe's accelerating expansion. Cold dark matter is the invisible substance whose gravity built the cosmic web. The lambda CDM model has been extraordinarily successful. It predicts the pattern of temperature variations in the cosmic microwave background with stunning precision. It predicts the large-scale distribution of galaxies. It predicts the abundance of light elements produced in the first 3 minutes after the Big Bang. But if the Hubble tension is real and the model cannot explain it, then somewhere inside the model, an assumption is wrong. Dark energy is the most likely candidate. The cosmological constant treats dark energy as a fixed, unchanging property of empty space. The same everywhere, the same at every point in cosmic history. But what if dark energy is dynamic? What if its strength varied over time, stronger in the early universe and weaker today, or vice versa? A dynamic dark energy would change the expansion rate at different epochs. The early universe calculation and the nearby universe measurement would naturally return different values because the expansion rate genuinely was different, and the model using a fixed dark energy cannot account for that difference. This is a theory, confirmed by nothing yet, ruled out by nothing yet, and it raises something that sits at the boundary between physics and philosophy. If dark energy is not constant, if it evolves over time, then the future expansion of the universe may be fundamentally different from what current models predict. Models say the universe will expand forever, eventually becoming cold, dark, and empty. If dark energy grows stronger over time, the expansion could accelerate past a critical point, tearing apart galaxies, then stars, then planets, then atoms themselves. Scientists call this possibility the Big Rip. If dark energy weakens over time, expansion could eventually slow, stop, and reverse. The universe could collapse back into an infinitely dense point, the Big Crunch. The Hubble tension is a gap of a few percent in two numbers, but the implications of that gap stretch to the end of time itself. While astronomers wrestle with the expansion problem, Webb has been producing a different kind of stunning image, one that confused the public and inspired a completely separate question about whether something in deep space is staring back. Gravity bends light. Einstein predicted this in 1915. Astronomers confirmed it 4 years later during a solar eclipse, watching starlight curve around the sun. The amount of bending was tiny, but in the deep universe, where the lensing object is an entire galaxy cluster containing trillions of times the mass of the sun, the bending becomes dramatic. When a massive galaxy cluster sits directly between Earth and a more distant galaxy, the cluster's gravity acts like a lens. It bends the light from the background galaxy around it in multiple directions. The bent light arrives at our telescopes from multiple angles simultaneously. Depending on the geometry, this produces arcs, multiple images of the same galaxy, or in perfect alignment, a complete ring of light. Scientists call the perfect ring an Einstein ring, a complete circle of light from a galaxy that sits directly behind the lensing mass. The geometry has to be close to perfect for the ring to close completely. Partial arcs are far more common. Webb captures these with extraordinary clarity. Its resolution and sensitivity reveal the fine structure inside these arcs, the individual star-forming regions in the background galaxy, the color of its oldest stars, the chemical profile of its gas. Gravitational lensing effectively magnifies distant galaxies beyond what Webb's mirror alone could resolve. Some of Webb's most striking images show multiple arcs surrounding a galaxy cluster, bright streaks of distorted light curving around a central mass. The cluster itself appears as a dense cloud of yellow and white galaxies. The arcs surrounding it glow orange and red, their ancient light stretched by both redshift and the additional distortion of lensing. These images circulate widely, and they tend to trigger a specific reaction. People see faces, eyes, pupils surrounded by glowing irises. The circular arrangement of a lensed galaxy around a central cluster does, from a visual standpoint, resemble an eye looking outward. The reaction is instant and human. The images feel like something is watching. Scientists confirm this feeling has a name and a reason, and the next chapter goes into why the human brain sees watchers in the ancient light of the cosmos, and what those shapes actually are. The human brain is a pattern detector. Evolution built it that way. In the environment where humans evolved, fast pattern recognition meant survival. Spotting a face in the shadows meant spotting a predator or an ally before it spotted you. The brain became tuned to find faces everywhere, to prioritize them, to see them even where they do not exist. Scientists call this tendency pareidolia, the phenomenon of perceiving meaningful patterns, especially faces or eyes, in random or abstract images. Clouds shaped like animals, toast that resembles a face, the image of a man on the surface of the moon. When Webb images of gravitational lensing spread across social media, pareidolia hits hard. The circular arcs around a central mass look like an iris around a pupil. The glow of a lensed galaxy behind a cluster resembles an open eye staring outward. Headlines call them cosmic eyes watching from deep space. The science is more grounded. The lensed light is ancient starlight, bent by gravity, curved around a galaxy cluster, containing trillions of stars. The circular shape has nothing to do with biological vision. It is a consequence of the geometry of mass and light. A ring forms because gravity pulls equally in all directions around a central mass, and when the alignment is right, equal pulling in all directions produces a circle. The background galaxy producing the ring is sometimes billions of light years behind the lensing cluster. Its light has been traveling for billions of years. It is ancient, passive, and completely unaware of the effect it creates when it reaches our detectors. But pareidolia reveals something important about how humans relate to astronomy. The face-finding instinct makes distant, abstract science feel personal. It makes the cosmos feel inhabited, watched, intentional. That feeling is not evidence of anything. The confirmed reality is that no eyes watch from the deep universe. The images are geometry and ancient starlight. What scientists do confirm is that gravitational lensing is one of the most powerful tools in astronomy. It lets Webb see galaxies that would otherwise be too faint to detect, even with its enormous mirror. Lensing boosts the apparent brightness of background galaxies, turning objects that should be invisible into detectable targets. Several of Webb's most significant early galaxy discoveries came from lensed fields, where the magnification of a foreground cluster pushed the background galaxies just above the detection threshold. The rings and arcs are tools, data, windows into a universe so old and so vast that the human brain keeps reaching for familiar shapes to make sense of the scale. And that instinct, the drive to find pattern and meaning, is also what pushes scientists to ask the deepest question Webb's data has raised. A question that starts with the structure of a black hole and ends with an idea about the entire universe that sounds more like science fiction than science. It is a confirmed theory, proposed by serious physicists, and it cannot be dismissed easily. Every black hole in our universe contains a singularity. A singularity is a point where density becomes infinite, where the known laws of physics break down completely. General relativity, the best theory of gravity humans have, predicts singularities but cannot describe what happens inside them. The math produces answers like infinity and zero in the same equation, which physicists recognize as a sign that the theory is hitting its limits. Some theoretical physicists have proposed a striking idea. The conditions inside a black hole's singularity, extreme density, extreme energy, the breakdown of known physics, resemble the conditions at the moment of the Big Bang. The proposal goes further. What if the Big Bang was not a beginning in an empty void, but the interior of a black hole that formed inside a larger parent universe? Our entire universe, everything Webb observes, every galaxy, every particle, every law of physics may exist as the interior of a black hole that someone or something in a larger universe would see as just another collapsed star. This is a serious theoretical proposal. Physicists Nikodem Poplawski and Lee Smolin have developed versions of it with real mathematical frameworks. The idea goes by various names, including the black hole cosmology hypothesis and the fecund universe model. The model predicts that every black hole in our universe spawns a new universe inside it. Our own universe spawned black holes, and each of those black holes contains a universe. The cosmos is nested, universe inside universe inside universe, each one created by the collapse of a massive star in the universe above it. Webb cannot confirm this. The model makes predictions that are difficult or impossible to test with any current instrument, because the hypothetical parent universe outside our own is separated from us by an event horizon we can never cross. No signal from outside can reach us, no signal from inside can escape to them. Confirmed, the mathematics behind this idea is real and published in peer-reviewed work. Confirmed, serious physicists engage with it. Unknown whether it is correct, unknown whether it will ever be testable. But Webb's observations of black holes in the early universe have added fuel to discussions about this model. The telescope found supermassive black holes at extremely high redshifts, black holes far larger than standard models predict for their era. If black holes seed new universes, then the early universe produced an enormous number of new cosmic births at a rate that current models had not anticipated. The idea that Webb is staring into a universe that is itself the inside of a black hole adds a layer of strangeness to every image it produces. Every ancient galaxy, every glowing ring, every distant dot of light exists inside a structure that from a larger perspective may look like a single collapsed star. Whether that is true or not, something inside our universe is causing expansion at a rate that our models cannot fully explain, and the substance responsible for that acceleration has never been directly seen. 68% of the universe is dark energy. Nobody knows what it is. That sentence is worth sitting with. The dominant component of the universe, the substance that controls its ultimate fate, the force that is accelerating the expansion of every galaxy away from every other galaxy, remains completely unidentified. Scientists confirm it exists, they confirm its effects, they cannot tell you what it is made of, or whether it is made of anything at all. Dark energy was discovered in 1998, when two independent teams of astronomers studied a specific type of exploding star called a Type 1a supernova. These explosions are useful because they always produce roughly the same peak brightness. By comparing how bright they look from Earth versus how bright they actually are, scientists calculate distances precisely. Both teams found that very distant supernovas were dimmer than expected. They were farther away than they should be if the universe were expanding at a constant rate. The universe was accelerating, something was pushing galaxies apart with increasing speed over cosmic time. Einstein had actually predicted this possibility decades earlier. His equations of general relativity allowed for a term he called the cosmological constant, a kind of energy inherent to empty space itself. He added it to make the universe static, then removed it when Hubble discovered the expansion, famously calling it his greatest blunder. The 1998 discovery essentially proved his blunder was correct. Empty space has energy. That energy pushes, and it wins over gravity at large scales and large distances, driving the universe apart faster and faster. Webb is actively studying dark energy by measuring how the cosmic web grew over different epochs of cosmic history. The rate at which galaxy clusters formed, the pattern of voids and filaments at different redshifts, all of this carries a record of how dark energy has behaved over billions of years. The Cosmos Web Survey provides exactly this kind of historical record. By comparing the cosmic web at redshift 2, corresponding to about 3 billion years after the Big Bang, with the web at redshift 5 or 6, much earlier, scientists track whether dark energy's influence was the same in the early universe as it is today. Early results suggest it may have varied. If dark energy was stronger or weaker in the past than it is now, that would explain part of the Hubble tension and require significant revision of the standard model. The honest scientific position is that dark energy is the biggest mystery in physics. Its nature is unknown. Its stability over time is uncertain. Its ultimate effect on the universe's future is unresolved. Webb is collecting the data needed to begin answering those questions, but the answers are not in yet. And while dark energy shapes the universe at the largest scales, Webb has been revealing something remarkable at the smallest observable scales. The way ancient light reveals what is hidden behind walls of cosmic dust that would block every other instrument ever built. Space is dirty, not in the way a room gets dusty. Cosmic dust is made of carbon compounds, silicates, tiny grains of material forged in the outer layers of dying stars and scattered by stellar winds and supernova blasts. This dust spreads through galaxies in enormous clouds, sometimes stretching for thousands of light years. Visible light cannot pass through these clouds. Stars hidden behind dense dust lanes disappear completely from optical telescopes. Entire regions of galaxies become invisible. Star-forming regions among the most scientifically interesting places in the universe are typically surrounded by the thickest dust because they form inside collapsing gas and dust clouds. The moment a star ignites, it sits inside a cocoon of the very material that created it. Hubble spent decades looking at the parts of galaxies it could see, while entire star-forming regions sat hidden a few thousand light years away, blocked by a wall of grains smaller than the width of a human hair. Webb sees through those walls. Infrared radiation, the type of light Webb detects, has wavelengths long enough to slip between dust grains rather than collide with them and scatter. The longer the wavelength, the better the penetration. Webb's mid-infrared instrument penetrates the densest dust clouds that completely block visible light. The result is a completely different view of the universe. When Webb pointed at the Carina Nebula, a region of active star formation about 7,600 light-years from Earth, it revealed an entirely new landscape. Hubble had photographed Carina before. The Hubble image showed dramatic cliffs of gas and glowing clouds. Beautiful and famous. Webb's infrared image showed something Hubble had completely missed. Hundreds of previously invisible young stars, newly ignited protostars, still embedded in their birth clouds. Plus, jets of material streaming away from infant stars in long, bright lines. An entire hidden population of newborn stars suddenly visible for the first time. This is repeated everywhere Webb looks. Galaxies that appeared smooth and simple in optical images reveal complex internal structures in infrared. Dust lanes that blocked the view of star-forming regions become transparent. The sensors of active young stars in nearby galaxies jumped significantly as Webb revealed populations Hubble could not see. For the most distant galaxies, this matters even more. Early galaxies were extremely dusty. The first generations of massive stars produced enormous quantities of dust through their explosions. That dust cloaked the galaxies, making them dimmer and redder in visible light. Webb sees through the dust cloaks and into the star-forming hearts of these ancient systems. The star formation rates calculated from Webb's infrared data are significantly higher in some cases than the rates estimated from Hubble's visible light data, because Hubble was missing the dusty, actively forming regions entirely. The universe has been hiding things behind a curtain of dust for billions of years. Webb is pulling that curtain aside one galaxy at a time. And in doing so, it is also revealing the true extent of the universe we can observe, a boundary that has nothing to do with dust and everything to do with the speed of light and the age of time itself. The observable universe ends at a boundary scientists call the cosmic horizon. Beyond that horizon, light has not had enough time to reach us. The universe is 13.8 billion years old. Light has been traveling since the Big Bang. The farthest light that has reached us started its journey at the moment the universe became transparent, about 380,000 years after the Big Bang. Everything beyond the distance that light has crossed in 13.8 billion years is invisible, and will always be invisible. But here is the thing that confuses almost everyone the first time they hear it. The edge of the observable universe is not 13.8 billion light years away. Due to the universe's expansion during those billions of years of travel time, the edge sits about 46 billion light years in every direction. The observable universe is a sphere with Earth at the center. Not because Earth is special, but because our position is where the observation happens. Any observer anywhere in the universe would see a sphere of the same size centered on themselves. Beyond 46 billion light years, galaxies exist, stars burn, planets form. Potentially, life arises. But their light will never reach us. The universe is expanding faster than light can close the gap between us and those regions. They are forever beyond our horizon, separated from us by a boundary that has nothing to do with walls or barriers, only time and speed. Webb is pushing as close to that horizon as possible. The galaxy, month over month, at redshift 14.4, formed when the universe was only 280 million years old, within the first 2% of cosmic history. Its light has been traveling for 13.5 billion years. It represents one of the most extreme objects inside our observable bubble. Are there galaxies that formed even earlier? Almost certainly yes. Galaxies from the first 100 million years of the universe may exist, but their light has stretched even further into the infrared, making detection harder. Webb's longest wavelength channels are pushing toward those limits. The cosmic horizon also means something strange about the future. As the universe continues expanding, galaxies that are currently at the edge of our observable bubble will eventually cross over our horizon. Their light will stop reaching us. The observable universe will slowly shrink from our perspective, not because space stops existing beyond the horizon, but because expansion pushes more and more of it past the point of no return. In the very distant future, a civilization in our galaxy would look out at a universe containing only the handful of galaxies gravitationally bound to our own. Every other galaxy would have crossed the horizon. The rest of the cosmos would be permanently dark and invisible. Webb is observing a universe that will become increasingly hidden over cosmic time. Every image it captures is a record of a universe we can see today, but will lose access to in the future. And what that universe looked like in its earlier stages keeps contradicting what scientists expected. The galaxies are too bright, too massive, too organized. A pattern of surprises that is forcing a reckoning with every model of cosmic evolution built before Webb launched. Something assembled the early universe faster than physics predicted. This sentence appears in research papers with increasing frequency since Webb began returning data. The specific claim varies by paper. Some focus on galaxy mass, some on star formation rates, some on the presence of supermassive black holes at extreme redshifts, but the pattern is consistent across all of them. The standard model of cosmic evolution, is called the Lambda CDM model. It predicts how structure grows from tiny density variations in the early universe. Those variations were small, about 1 part in 100,000 in density from one region to another. Over billions of years, gravity amplified those variations. Slightly denser regions pulled in more matter, less dense regions emptied out. Galaxies, filaments, and voids grew from these seeds. The model makes specific predictions about how much mass should be in galaxies at different epochs. At redshift 10, a galaxy formed just a few 100 million years after the Big Bang. The model predicts mostly low-mass systems still building their first generations of stars. Webb found galaxies at redshift 10 that are far more massive than predicted. Multiple galaxies, consistently above the expected mass range. One candidate, nicknamed the Cosmic Behemoth by the team that found it, showed a stellar mass roughly 100 times higher than the model allows for that redshift. Scientists immediately applied scrutiny. Mass estimates for distant galaxies carry significant uncertainty. Assumptions about stellar populations, dust content, and star formation history all affect the calculation. The Cosmic Behemoth's mass could be lower if some of those assumptions are revised. But even with conservative estimates, the most extreme early galaxies in Webb's data remain above the predicted range. The overshoot is real even if the exact magnitude is uncertain. The black hole problem is even sharper. Supermassive black holes at the centers of galaxies should grow gradually over hundreds of millions to billions of years. They feed on surrounding gas, growing with each meal. The standard model predicts that the largest black holes at very high redshifts should be relatively modest in mass, because they have not had time to grow large. Webb found a black hole at redshift 6.6, corresponding to about 800 million years after the Big Bang, with a mass about 1 billion times the mass of our Sun. And another at even higher redshift, showing similar excess mass. These black holes should not be that large. The feeding process simply has not had enough time. Scientists have proposed possible mechanisms. Direct collapse black holes formed not from stellar explosions, but from the direct gravitational collapse of an enormous gas cloud could produce a large seed black hole quickly. Rapid early feeding driven by the extreme gas densities of the early universe could accelerate growth beyond the standard rate. These are theories, plausible, consistent with some data, not yet confirmed. The consistent pattern is that the early universe filled up faster than expected. Stars, galaxies, black holes all grew to significant sizes during the cosmic dawn, at rates that current theory struggles to explain. And one consequence of all that early star formation is something that connects the beginning of the universe directly to the composition of every living thing on Earth. The most distant galaxies in Webb's data glow too bright. Astronomers expect it faint. Galaxies from the cosmic dawn should look dim. They are 13 plus billion light years away. The inverse square law governs how light spreads across distance. An object twice as far away appears 4 times dimmer. An object 13 billion light years away should be almost invisibly faint. Some of them are brighter than that math allows. The excess brightness shows up in specific wavelength bands, corresponding to the infrared emissions from hot young stars. Stars that are massive, young, and burning at extreme temperatures pour out enormous ultraviolet radiation. That radiation, redshifted by the expansion of the universe across 13 billion years, arrives at Webb's sensors in the infrared. The signal is stronger than expected, more energetic than models predict for galaxies of that age. An estimated mass. Several explanations are possible. The initial mass function of stars in the early universe may differ from today. The initial mass function describes the distribution of stellar masses produced when a new generation of stars forms. Today, most new stars are smaller than the Sun. But in the early universe, with different gas temperatures, different chemical compositions, and different pressures, the distribution may have favored more massive stars. More massive stars burn hotter and brighter. They produce more ultraviolet radiation per unit of stellar mass. If early galaxies produced a higher fraction of massive bright stars than today's galaxies do, they would appear more luminous than models based on current stellar populations predict. Another possibility involves the escape fraction of ionizing radiation. Massive stars produce radiation energetic enough to strip electrons from hydrogen atoms, creating ionized hydrogen that glows in specific wavelengths. Inside a typical modern galaxy, much of that radiation is absorbed by surrounding gas and dust before it can escape. In early galaxies, which may have been less dusty and more porous in structure, more of that radiation escaped into the surrounding space, making the galaxies appear brighter in specific observational bands. Astronomers distinguish between these scenarios by measuring the detailed spectra of early galaxies, looking for specific emission lines that indicate which physical process dominates. Webb's spectrograph is doing exactly this work right now, for dozens of early galaxies, building up a statistical picture of how star formation operated in the cosmic dawn. The brightness excess is a clue, and every clue about what early galaxies looked like is also a clue about what the first stars were like, because every atom of every element heavier than hydrogen in those early galaxies came from a star that had already lived and died. The chemical fingerprints left by those first stars in the early galaxies are also the chemical fingerprints left in every planet, every ocean, every living cell that formed in the universe after them. The elements Webb detects in a galaxy 13 billion light years away are the same elements your body is built from, same stellar forges, same explosive deaths, same scattering of atomic material into the gas clouds that eventually built everything. And that chain of chemical inheritance raises the final and most profound question Webb is working toward answering. You are made of stardust. This phrase gets repeated so often, it lost its meaning somewhere along the way. But Webb's data restores that meaning with specifics sharp enough to feel real. Every hydrogen atom in your body formed in the first 3 minutes after the Big Bang. The Big Bang produced hydrogen and helium, nothing heavier, no carbon, no oxygen, no nitrogen, no iron, no calcium. Just the two lightest elements plus a tiny fraction of lithium. For the first few 100 million years, the universe contained only these light elements. Everything heavier had to be made somewhere. That somewhere is a star. Inside a star's core, nuclear fusion fuses lighter elements into heavier ones. Hydrogen fuses into helium, helium fuses into carbon, carbon fuses into oxygen, oxygen fuses into silicon. In the most massive stars, silicon fuses into iron. Iron is the end point. Fusing iron consumes energy instead of releasing it. The fire goes out, the core collapses, the star explodes. In that explosion, elements heavier than iron form rapidly through a process called neutron capture, where atomic nuclei absorb neutrons faster than they can decay. Gold, uranium, iodine, and dozens of other heavy elements form in seconds during the supernova. The explosion scatters them into the surrounding gas. The calcium in your bones came from a supernova. Confirmed. The iron in your blood came from a stellar collapse. Confirmed. The oxygen in every breath came from the nuclear fusion happening inside stars that died before the sun formed. Confirmed. Webb's earliest galaxy observations push this story back further. The nitrogen anomaly in Month Over Month and other early galaxies reveals that the very first stellar generation, the massive short-lived stars of the cosmic dawn, produced heavy elements and scattered them into the surrounding gas within the first few 100 million years of cosmic history. Some of that scattered material ended up in later galaxies. Some ended up in the gas cloud that eventually collapsed into the Milky Way. Some ended up in the molecular cloud that formed the sun and its planets. 4.6 billion years ago, some of it ended up in you. The carbon in your cells traces back to the fusion happening inside stars that exploded before Earth existed. The atoms in your fingernails passed through at least one supernova, possibly several, before arriving in a solar nebula and eventually becoming part of a living thing on a rocky planet around an ordinary star. Webb is reading the chemical record of those ancient stellar generations in the spectra of galaxies over 13 billion light years away. The fingerprints of the first stellar deaths are preserved in the light from the cosmic dawn. And that raises a question that Webb is uniquely positioned to probe. A question about how far back the stellar generations go. Whether a galaxy exists at a redshift so extreme that its light carries signatures from stars that formed before any other generation. Whether the very first stars are detectable, or whether Webb will eventually find something so far back that it contradicts the entire timeline of the Big Bang. Every few months, a headline appears claiming that Webb has broken or disproved the Big Bang. Every time, astronomers correct it. The Big Bang is confirmed by multiple independent lines of evidence so robust that no single telescope observation is going to overturn it. The cosmic microwave background, the abundance of light elements, the observed expansion of the universe, all of these fit the Big Bang model precisely. Webb is not challenging the Big Bang. What Webb is challenging is the standard model of galaxy formation within that framework, the lambda CDM model. And there is a genuine difference between those two things. The Big Bang is the event. The lambda CDM model is the description of how structure grew after that event. The first is firmly established. The second is a working model that the science community has built up over decades and continues to refine. Webb is refining it aggressively. The overly massive early galaxies, the overly bright star formation rates, the overly large early black holes, the nitrogen anomaly, all of these are challenges to the lambda CDM model's specific predictions. Scientists who study these results are modifying assumptions inside the model, not discarding the framework entirely. But there is a limit to how many modifications a model can absorb before scientists begin to consider that the framework itself needs replacement. That limit has not been reached. Astronomers are still in the adjustment phase, changing assumptions about dark matter properties, stellar populations, black hole seeding, and gas physics. Each adjustment brings some data into better alignment. New data from Webb immediately tests the revised model. The genuine breaking point would come if Webb confirmed a galaxy with a redshift above 20, corresponding to a galaxy that formed less than 180 million years after the Big Bang. Or if the chemical profile of an early galaxy showed heavy elements that simply could not have formed in the time available under any version of the standard model. Nothing at that level has been confirmed yet. The candidates exist. Webb continues looking. Scientists are clear on one thing. If a discovery of that magnitude came in, it would not disprove the Big Bang. It would require a fundamental revision of how rapidly structure formed immediately after the Big Bang, which might point to changes in the assumed initial conditions, the properties of dark matter, or even the physics of inflation. The rapid expansion event thought to have occurred in the first fractions of a second after the Big Bang. The universe at the cosmic dawn is a testing ground for physics at its most extreme. Webb is the first instrument powerful enough to observe that testing ground directly. And everything it finds there is forcing a reckoning with the models. A reckoning that will either refine the standard picture or replace it with something more accurate. Whatever comes next will require a new generation of instruments. Instruments already being designed right now, informed by every anomaly Webb has uncovered. Webb has been operational for less than 5 years. In that time, it has already forced changes to specific scientific models that have been stable for decades. The first revision hit the model of reionization. After the cosmic dark ages, when the first stars switched on, their radiation began ionizing the hydrogen gas filling the universe. This process, called reionization, gradually changed the universe from a foggy state where light scattered in every direction to a clear state where light could travel freely. The standard timeline placed the end of reionization at about 1 billion years after the Big Bang. Webb's observations of the most distant galaxies confirmed that galaxies from the cosmic dawn were producing ionizing radiation at much higher rates than expected. The reionization process may have completed earlier than the standard model predicted, driven by a larger population of early galaxy ionizing sources than the old model accounted for. The second revision involves the number density of early galaxies. Early galaxy count predictions from lambda CDM were used to plan Webb's observation programs. Scientists expected to find a certain number of early galaxies above specific brightness thresholds. Webb found more, Significantly more, the early universe contained more galaxies, or brighter galaxies, or both, than the pre-Webb predictions said it should. Textbooks and review articles that describe the expected galaxy population at high redshift now carry notes and revisions. Some have been replaced entirely in online versions. The third revision touches the assumed relationship between galaxy mass and star formation rate. Standard models predicted that star formation in early galaxies follows a relatively smooth relationship with total stellar mass. Webb data shows scatter in that relationship far beyond what the models allowed, suggesting that early galaxies experienced episodes of rapid star formation followed by sudden suppression, a boom and bust pattern that the smooth model did not capture. Understanding what caused the suppression is a major open question. When early galaxies suddenly stop forming stars, something quenches the process. Candidates include intense radiation from a central black hole, heating the gas and preventing it from cooling into new stars, or supernova feedback blasting gas out of the galaxy entirely. Webb is observing galaxies in the process of quenching, catching them in the act of shutting down their star formation. The spectra of these galaxies show the signatures of a sudden transition: hot stellar populations fading, emission lines weakening, the light shifting toward older stellar populations over just a few 100 million years. Every one of these revisions happened because Webb provided data at redshifts and sensitivities no prior instrument could reach. Each revision points toward a universe that assembled faster, burned brighter, and evolved more dramatically in its youth than the models built before Webb predicted. The models have absorbed these hits and been strengthened by the revisions. The scientific process is working, but the rate of discovery shows no sign of slowing, and the questions Webb has raised are large enough that answering them will require more than any single telescope can provide. The next chapter of this story belongs to instruments still being built, instruments designed specifically to answer the questions Webb raised but cannot solve. Webb changed astronomy. The question now is what comes next. Several next-generation telescopes are in development, each designed to push past one of the specific limits Webb exposed. The anomalies Webb found, the overly massive early galaxies, the Hubble tension, the nitrogen anomaly, the early black hole excess, all of these require more data, sharper resolution, or different wavelength coverage than Webb can provide. The Nancy Grace Roman Space Telescope is the most imminent. Scheduled to launch in 2027, it will observe invisible and near-infrared light, with a mirror similar in size to Hubble, but a field of view 100 times wider. Roman will survey enormous areas of sky to build statistical samples large enough to pin down dark energy's behavior over cosmic time. Where Webb goes deep and narrow, Roman goes wide. Together, their datasets are designed to complement each other. Roman's wide-field surveys will map hundreds of millions of galaxies, tracking how their distribution changed across billions of years of cosmic history. That distribution carries the imprint of dark energy's influence. By comparing the observed distribution against model predictions at different epochs, Roman will test whether dark energy is constant or variable, with a precision Webb cannot match. On the ground, the extremely large telescope is under construction in the Atacama Desert in Chile. Its primary mirror will stretch 128 feet across, making it by far the largest optical and infrared telescope ever built. It will collect so much light that it can take spectra of individual stars and galaxies millions of light years away, and detailed spectra of distant galaxies Webb can only image as red dots. The extremely large telescope's spectroscopic power will allow scientists to confirm or revise the mass estimates of the earliest galaxies Webb has flagged as anomalous. It will measure chemical abundances in early galaxy spectra, with a precision Webb spectrograph cannot reach at those distances. It will directly test the nitrogen anomaly in dozens of early galaxies, rather than the handful Webb has managed. Further ahead, space agencies in the United States, Europe, and Japan are studying concepts for a successor to Webb. Names like the Habitable Worlds Observatory and the Large Ultraviolet Optical and Infrared Surveyor appear in planning documents. These would combine Webb's sensitivity with wider fields, broader wavelength coverage, and the ability to study the atmospheres of rocky planets around nearby stars, searching for chemical signatures of life. The questions Webb raised about the universe's origins connect directly to the question those future telescopes will address. If the first stellar generation produced the building blocks of chemistry so rapidly, if galaxies assembled so quickly from those building blocks, then the conditions for planets and for life may have appeared earlier in cosmic history than anyone predicted before Webb launched. Webb showed us a universe more active, more complex, and more surprising in its youth than a generation of astronomers expected. The models it broke are being rebuilt. The questions it raised are being turned into the design requirements for the instruments that come next. Every red dot in Webb's deep field images is a question. Every nitrogen anomaly is a gap in the story. Every overly massive early black hole is an invitation. The universe spent 13.8 billion years building the atoms, the stars, the galaxies, and the planet that produced a species curious enough to aim a golden mirror at the edge of time and ask, what is out there? The answer, so far, is that the universe is stranger, older, and more alive in its past than we imagined, and we are only just beginning to read it.